All right, let's dive right in. Today, we're going to peel back the curtain on reality itself. I mean, what if I told you that the rules you see and experience every single day just don't apply at the smallest scales? We're about to explore the bizarre, the counterintuitive, and, let's be honest, the downright weird rules that actually run the universe. Yep, we're heading straight into the world of quantum mechanics.
And look, don't just take my word for how strange this all is. The source material for this puts it perfectly. This stuff represents perhaps the deepest mystery in all of science. So we're not just dipping our toes into some obscure corner of physics here. No, we are tackling what might be the biggest, most profound puzzle scientists have ever run up against. It's a world that completely defies common sense, but, and this is the crazy part, it's been tested and proven right over and over and over again.
Okay, so the world we know, the rules of everyday life. Before we can really appreciate just how bizarre the quantum world is, we've got to first get a solid grip on the world we think we know. You know, the classical, predictable one we live in every single day.
So in our normal, everyday world, what we call the state of something is, well, it's pretty simple, right? It's just a complete description of it, all of its exact properties. For any object you can think of, you can know exactly where it is and exactly how fast it's going at the exact same time.
Yeah, think about a baseball flying through the air. At any single moment, that ball has one specific position and one specific speed. And here's the key, it doesn't matter if you're watching it or not. Those properties are just there. They're fixed. They're real. And we can know both of them.
And what's cool is that once you know that basic state, the position and the velocity, you can figure out basically everything else about it. Its kinetic energy, its momentum, all these other observables just fall right into place. You can calculate them with total 100% certainty. It's predictable. And you know what? It's kind of comforting.
All right, you ready? Let's take that first quantum leap into a world of pure possibilities. Because this is where everything we just talked about gets thrown right out the window. It's about to get really, really strange.
So what does a state even mean in quantum mechanics? Well, forget about a neat list of definite properties. A quantum state is all about probabilities. That's it. It's a list of possibilities. It doesn't tell you where a particle is, it only tells you where you might find it if you go looking. We're moving from a world of certainty to a world of pure potential.
And this brings us to one of the most famous and frankly weirdest ideas in all of science, superposition. Get this, a particle, like an electron, isn't in one single place. No, it exists in this sort of blurry haze of all its possible positions, all at the very same time. It's like it just hasn't made up its mind where it wants to be yet.
I mean, just look at the difference side by side. It's a completely different way of looking at reality. In our classical world, a particle has a position. It's a done deal. Its properties are fixed. But in the quantum world, a particle exists in a superposition of many positions. Its properties are nothing but a haze of probabilities, just waiting for us to look.
Okay, next up, the act of measuring, or as I like to call it, forcing reality's hand. This begs an obvious question, right? If a particle is just sitting there in this fuzzy cloud of possibilities, what in the world happens when we actually try to, look at it? What happens when we measure it?
And this right here is one of the most mind-bending parts of this whole thing. In quantum mechanics, looking isn't a passive activity. Not at all. The very act of measurement forces the system to choose. It snaps out of that fuzzy superposition and collapses into one single reality. You don't just discover where the particle is, you actually force it to pick a spot.
So let's walk through an example. Imagine an electron. Before we look, its spin is in a superposition. It's both spin up and spin down at the same time. It's totally indeterminate. Then, step 2, we decide to measure it. Boom! The moment we do, the state randomly collapses. It's forced to become either spin up or spin down. And just like that, the measurement's done. We now know its spin for sure. But the catch is, by forcing that one answer, we might have just messed up our ability to know something else about it.
And you have to understand, this isn't some problem with our equipment. It's not like if we just built a better measuring device, we could predict the outcome. Nope. The source material is crystal clear on this. The randomness is inherent. This uncertainty is baked right into the DNA of the universe itself. It's a fundamental feature of how reality works. Which brings us to our next big idea, a rule of uncertainty, or what you can think of as the ultimate trade-off. Because this active role of measurement, well, it leads to a hard limit on what we can ever know about a quantum system at any one time.
So in the quantum world, it turns out it just can't know everything about a particle all at once.
Some properties are compatible. Think of them as partners. You can know both of them with perfect certainty. But, and this is a huge but, a lot of the most important properties are not compatible. They're like rivals.
And this table right here shows that trade-off perfectly. Now don't get bogged down by the math in the middle. That's not the important part. Just look at that compatible column on the right. If we measure an electron's spin on one axis, let's call it the z-axis, we get a definite answer. Yes, it's compatible. But look what happens to the other axes, x and y. They're both a no. The instant we lock down the spin on the z-axis, the spin on the other two becomes completely, totally random. A 50-50 coin flip. You can't know them all. Measuring one scrambles the others.
And all of this leads to probably the most famous principle in all of quantum mechanics, the Heisenberg uncertainty principle. And it's really the ultimate consequence of everything we've been talking about. It says that the more precisely you pin down a particle's position, the less precisely you can possibly know its momentum. And it works the other way around, too. Know the momentum perfectly, and its position becomes a complete blur. You can never, ever know both with perfect precision. It really is the universe's ultimate trade-off.
So, from the weird to the wired, why does any of this matter? I know what you might be thinking. This is all just a fascinating, strange, philosophical puzzle, right? But the truth is, these bizarre quantum rules are not just theory. They have an absolutely profound impact on the world you're living in right now.
Seriously? Our entire modern world is built on this stuff. The transistors inside the device you're watching this on, they only work because we understand quantum mechanics. Lasers? That's all about manipulating quantum energy levels. Those life-saving MRI scanners in hospitals, they're using the quantum spin we just talked about. Even GPS relies on it. From the computer chip to the dream of quantum computing, all of these technologies exist because we learned how to harness these incredibly strange rules.
So yeah, these bizarre rules are so much more than just a philosophical curiosity. You could honestly say they are the engine of the 21st century. The very strangeness that makes this stuff so hard to wrap our heads around is exactly what makes our modern, high-tech world possible.
And that leaves us with one last really big question to chew on. If the only reason a quantum system picks one definite reality is because we measured it, then what is the universe actually doing when nobody's looking? What is the true nature of reality? Is it just this shimmering sea of possibilities waiting for an observer to show up? That is a question that, to this day, keeps physicists and philosophers up at night.